Comparison between isothermal and adiabatic process. These are the pressure volume graphs for isothermal as well as adiabatic processes. This is expansion, this is compression. Expansion happens from V1 to V2. So always remember this, always slope of adiabatic curve is more than slope of isothermal curve. I am repeating, slope of adiabatic curve is more than slope of isothermal curve. Therefore, number 2 has more slope, so it is adiabatic. Number 1 has less slope, so it is isothermal. In this case, number 1 has more slope, therefore it is adiabatic. Number 2 has less slope, therefore it is isothermal. These two are compressions from V3 to V4. Area under the graph is the work done. Therefore, work done in isothermal is more than adiabatic. Pressure in isothermal is greater than pressure in adiabatic at the final stage, and temperature of isothermal system is greater than temperature of adiabatic system. Then, for the same compression, work done is more in adiabatic because adiabatic is above isothermal, and area under the curve is the work done. Area is more under the adiabatic, therefore more work. Pressure in adiabatic is more because this point is taller than this point. This point is taller than this point. And temperature at the end is more for adiabatic compared to isothermal. Then, for free expansion means expansion against zero pressure. For free expansion, work done is 0. External pressure is 0, therefore work done is 0. Energy is not provided to the system, therefore delta Q is also 0. If delta Q, delta W both are 0, then delta U is also 0. Therefore, internal energy in free expansion does not change. Internal energy does not change means temperature remains same in free expansion. Ideally, but in real cases, temperature decreases. In free expansion, in real cases, temperature decreases. Ideally, temperature should remain same. Then, cyclic and non-cyclic processes. If system returns back to its initial state, then it is called cyclic process. If system returns back, then it is called cyclic process. If system returns back to its original state, that means initial temperature and final temperature both are same. Therefore, change in internal energy is 0. So, as per the first law, delta Q is equal to delta W. Then, area enclosed by PV graph is work done. If process is clockwise, then work done is positive. If process is anti-clockwise, then work done is negative. For non-cyclic process, work done is calculated like this. If process goes from first point to second point, if process goes from initial point to last point, then we have to draw two vertical lines. We have to draw two vertical lines from point 1 and point 2. Here both lines are overlapping, and we have to find out enclosed area. This is the enclosed area, that is the work done. If process goes from this point number 3 to number 4 point, then we have to draw vertical lines from those points, and area enclosed is the work done. Here process is anti-clockwise, therefore work done is negative. Here work done is positive because process is clockwise. Then quasi-static process. If process is nearly in thermodynamic equilibrium at any instant, then the process is called quasi-static. P, V, T are unique at any instant. P, V, T are unique at any instant. Then reversible process. Process which can be reversed in such a way that all changes occurring in the direct process are exactly repeated in opposite order. So reversible process means reverse process should be possible. First, reverse process should be possible, and second, changes happened in first process should be exactly same and exactly opposite of changes in the reverse process. Means if we are if we have gone from state 1 to state 2, if we have gone from state 1 to state 2, so it should be possible for us to come from second state to first state, and then changes in first process in forward process should be same as changes in reverse process. So if energy provided in first process, forward process, is delta Q, then energy provided in reverse process, process second, should be minus delta Q. If work done in forward process is delta W, then work done in reverse process is minus delta W. Same with the internal energy change. Then reversible process should not have friction, viscosity or electrical resistance. Process should be slow. For it to be reversible, process should be slow. Then isothermal and adiabatic processes, if performed slowly, then they are reversible. Water to ice, ice to water conversion is reversible. Slow evaporation and slow condensation is also reversible. Then irreversible processes, processes which are not reversible are irreversible. Damped vibrations, sudden processes, current passing through the resistance, these are irreversible processes. Then graphical representations, these are pressure versus volume graphs. So graph number 1, vertical line, is isochoric process, isochoric, volume same. Graph number 4 is isobaric process, pressure constant. Graph number 3 and 2 are either isothermal or adiabatic. Number 2 is adiabatic because more slope. Number 3 is isothermal because less slope. Then pressure versus temperature graphs. Vertical line is isothermal. Horizontal line is isobaric. For this line, relation between pressure and temperature is linear, which means constant volume. Constant volume means isochoric. And this is the remaining process then. Then for volume versus temperature graph, number 3 is isothermal, number 1 is isochoric, number 4 is isobaric, and number 2 is adiabatic. Here number 3 is adiabatic. Heat engine converts heat into work. It is made up of source, sink and working substance. Source is reservoir of heat at high temperature. Any amount of heat extraction does not change its temperature. Any amount of heat extraction does not change its temperature. Working substances are steam, petrol or diesel. Then sink, reservoir of heat at low temperature. Sink is what? Reservoir of heat at low temperature. Any amount of heat can be given to the sink without changing its temperature. Heat engine is like this. This is the heat engine. It gets heat from the source Q1. It loses heat to the sink Q2. And difference between Q1 and Q2 is the work done. Suppose this heat engine is engine of the bike. So it gets energy from the petrol. It gets Q1 energy from the petrol. It gives out some energy to the atmosphere. Atmosphere is the sink. It gives out some energy to the atmosphere because engine is very hot. It loses some energy through radiations, through convection, through conduction. That lost heat is Q2, and remaining heat is used to take vehicle from one place to another place. That is work done, Q1 minus Q2. Efficiency is work upon Q1, work done upon Q1, heat provided. Efficiency is Q1 minus Q2 upon Q1. Then refrigerator or heat pump. Heat engine which runs in reverse direction is called a refrigerator or heat pump. Here source is at high temperature T1. Working substance here is refrigerant, liquid ammonia or freon, and sink is at low temperature. So this is the refrigerator diagram. It takes away heat from the sink. Sink means refrigerator. It takes away heat from the sink and it gives out energy to the atmosphere. And for this it needs electrical energy, that is called W. It needs electrical energy. It takes Q2 energy. If it is 50 joules, it takes 50 joules out of the fridge and gives out 70 joules to the atmosphere. So what about 20 joules? It gets 20 joules from the electricity. So it removes Q2 energy from the sink, it gives out Q1 energy to the atmosphere, and work done means energy provided by electricity to the fridge is Q1 minus Q2. Here coefficient of performance is calculated. It is Q2 upon work done or Q2 upon Q1 minus Q2. Q2 upon Q1 minus Q2. For Carnot refrigerator, coefficient of performance is this: T2 upon T1 minus T2. Source temperature, sink temperature. Relation between coefficient of performance and efficiency. Beta is equal to 1 minus eta upon eta. Then Carnot engine, second law of thermodynamics and Carnot engine. Then Clausius statement. It is impossible for a self-acting machine to transfer heat from a colder body to hotter one without the aid of an external agency. It is impossible to transfer heat from colder body to hotter body without the help of external agency. Entropy of the universe always increases with time. Then Kelvin's statement. A Carnot engine cannot work if the source and sink are at same temperature. Then Kelvin Planck's statement. It is impossible to design an engine that extracts heat and utilizes it fully into work without producing any other effect. Simple meaning of this is to transfer heat from low temperature to high temperature. What I am saying, to transfer heat from low temperature to high temperature, energy is needed. Energy is needed. Then Carnot engine. It is the standard against which the performance of an actual engine can be judged. Carnot engine has highest efficiency. Every real engine has less efficiency compared to Carnot engine. Carnot engine is like this. It is made up of these four parts. First one is cylinder having insulator, walls, insulator, and these walls are